Hi everyone. This is a lesson on definite integrals. We're going to review definite integrals. We've gone over it briefly already, and then I want to also add finding definite integrals using U substitution. And then the graphic at the bottom of the screen once again illustrates the geometric and analytic representations of integrals. Remember, integrals are just the area under a curve. That's geometric, and then you can see the formula here, the notation that we use to represent a definite integral. So once again, this graphic shows a definite integral as opposed to the definite integral as a function of x. So we're going to talk a little bit about this part, but mostly we're going to concentrate on the definite integral as a number. Notice that you have a constant to a constant of a function. F is a function of x, right? So this is the definite integral, and the result of this integral is going to be a number. On the definite integral as a function of x, I have a constant to x. Notice that this is a big F, and so it's the antiderivative of f of t dt. This is a new variable. F is a function of t. So this is the definite integral as a function. This is the fundamental theorem of calculus. And so if you were to integrate this, you would actually end up with this variable in the f function. Okay, so when we're finding a definite integral from a constant to a constant, the result is going to be a number. So you're actually going to end up with a number. So we can see this is a polynomial. This is easily I'm going to take the integral just the normal way. So e to the 3x to the third over 3 plus 5x squared over 2 minus 4x. Only this time, instead of plus c, I'm going to take that integral from 1 to 3. So in order to do that, you start with the top number. So this is just x to the third, right? That cancels. So I would have 3 to the third plus 5 halves 3 squared minus 4 times 3, right? That's just putting 3 in for it. Then minus, and I'm going to put a parenthesis. This would be 1 plus 5 halves minus 4. Okay, and so that would take a little bit of time to figure out. 27 plus 45 over 2 minus 12 minus, and then I'm going to have negative 4 plus 1 is negative 3, so I would have negative 3 plus 2.5, so that would be negative 1/2, so that would be plus 1/2, and so then when you look at that, 45 plus 1/2, and I'm not even sure I'm getting the right answer, 46 over 2 is 23, so 27 plus 23 minus 12, I can't resist 38. And I actually stopped the video and worked it on the calculator, and it literally is 38. I feel vindicated. So here's another example using trig functions. And so if I take the integral of this, I have x minus cosine x from 0 to pi. And so that's going to get me pi minus the cosine of pi, and then minus, in parentheses, 0 minus the cosine of 0. And so I'm going to have pi. Cosine of pi is negative 1, so a negative 1 is plus 1. The cosine of 0 is 1, so I've got plus 1. And so that's going to get me pi plus 2. So now we've added u substitution. We've done this. This is still an indefinite integral, and so we want to find u, and we know that u is usually something to a power, and that's going to be sine 3x. Right? I'm writing the cosine 3x dx together. My u is going to be sine 3x, so du is going to be cosine 3x times 3, right? Chain rule, dx. So I'm missing a 3. I need to add a 1/3 out here because 1/3 times 3 is just 1. And then I'm going to rewrite as a u substitution problem. So I have u to the second du. I end up with u to the third over 3. Now I'm just going to bring this down. This is 1/3, not 3, 1/3. So this is u to the third over 9. plus c, and u is sine 3x. So what we have going on here is that we don't have a definite integral. I could find a definite integral, but because I'm having to use a u substitution, it is actually going to change what these signs on here are. That looks like an e, but it's not. Okay, so here we go. So the general power rule looks like this. I've got two different ones. Notice that this one, the first one, has an x in the front. This one does not, right? So if I were doing u substitution on this one over here, u substitution, u would be x squared plus 1, the inside, you know, and then du would be 2x, right? 2x dx. And so I could rewrite that as something to a power with an x dx over here, right? X squared plus 1. And then I know I would have to add the 2, so I add the 2 and the 1/2. And then, you know, skipping a few steps, I would have the inside, x squared plus 1 to the third over 3 times the 1/2. And then, so I would have x squared plus 1 to the third over 6 plus c. Right, now, u substitution won't work on this one. But I could just multiply it out, right? And then I would get x to the fourth plus 2x squared plus 1 dx, and then integrate separately. So x to the fifth over 5 plus 2x to the third over 3 plus x plus c, and I'd have it. So I don't always need u substitution, but when it works, it makes things a lot easier. So u substitution is often called change of variables, and we've called it u substitution. The book calls it change of variables. It's the same thing. And so we've talked about how we work with u substitution with an indefinite integral. Now we want to talk about it with a definite integral. And remember that a definite integral is the area under the curve between two values. So we're actually computing the area under the curve, the actual area under the curve, instead of finding a function that does that. All right, so on here, let's look at the theorem. It says if the function u equals g of x has a continuous derivative on a closed interval and f is continuous on the range of g, then the definite integral of this composition function, right, this composition function is this with the new interval f of u du. So this is still the u substitution here, but these are going to change. The interval is going to change. So here is my, this is my u substitution from the last page, right? This was 0 to 1, only we've added now from 0 to 1 of this function. So we saw it worked on the previous. So evaluate, we're going to let u be x squared plus 1. We've obtained this, right, and this is this. And then before substituting, I'm going to make new upper and lower limits of integration. All right, so what is g of x? Well, g of x is the u. So here is g of x. So what I need is I need g of the upper limit, 1, and I need g of 0. And those will be my new limits. So I do 1 squared plus 1, which is 2. I do 0 squared plus 1, which is 1. And then I'm going to evaluate the integral, keeping the u in it instead of replacing the u with a value. So I have from 1 to 2, right, of u to the third du. Now remember over here that I had to add a 1/2, right, because du of the inside was a 1/2, so this is still 1/2, right, but I'm going to evaluate this. I am not going to substitute for the u. So I'm going to have u to the fourth over 4 times 2, which is 8, and I'm going to evaluate this from 1 to 2, right? So this is going to get me 2 to the fourth over 8 minus 1 to the fourth over 8, which is 16 over 8 minus 1 over 8, which is 15/8. Okay, so if I had done the evaluation using the u substitution, that I had substituted all of that back in, I would still have gotten 15 over 8. So in other words, if I had used this 0 to 1 of, and I'd done this u to the third du, and then had substituted here, instead of using the u, I would have still ended up with 15/8. Okay, but we do need to practice changing the variable for the definite integral. Okay, so here's an example, another example of a u substitution, a change of variables problem. We are going to set u equal to the part that's to the second power, 2x to the fourth plus 1. Du would be 8x to the third dx. If I rewrite this, and I'm going to write it as an indefinite, I would have something to the second power, x to the third dx. I'm going to add the 8, so that would give me a 1/8 out here. And then the other thing that I have to do is I have to find my new, these new values here. So I'm going to take g of x is going to be equal to the u, 2x to the fourth plus 1. I need g of 1, which is 2 plus 1, which is 3. And then I need g of 0, which is 1. And those are going to be my new integration. So as I write this as a u substitution, I have 1/8 from 1 to 3 of u to the second du. And all of that is substitution. And that just comes straight down. And then remember, we needed a new set of to go between because we are doing the composition function on the inside. So I'm going to integrate u to the third over 3 times 8 is 24, and I'm going to do that from 1 to 3. And so I'm going to end up with 3 to the third is 27 24ths minus 1 24th, which is 26 24ths, which if I divide by 2 is 13 12ths. One last example, and this is from your book, but it doesn't have to be to a whole number power. It could be a square root or a cube root that you could also do. So my u is still what's under the square root, 1 minus x squared. Du is negative 2x dx. Okay, so if I start to rewrite this, I'm going to have something to the 1/2 power, and then my x dx is over here. It's negative 2, so I'm putting a negative 1/2 out here. And then I also know that g of x is equal to my u. So I need g of 1, and I need g of 0. So if I put a 1 in there, 1 minus 1 is 0. A 0, 1 minus 0 is 1. So that's going to kind of turn things around a bit. All right, so I've got the negative 1/2. This time, instead of the 0, I have a 1. Instead of the 1, I have a 0, which is interesting. Then I have u to the 1/2, and then this is du. Integrate. So I've got 1/2 plus 1, which is 3/2, to the 2/3, because I'm dividing by 3/2, so I multiply by 2/3, times negative 1/2. And I have basically negative 1/3 u to the 3/2 from 1 to 0. Okay, so that's I'm going to put the 0 in first, so I'm going to have 0 minus, and then in parentheses, negative 1/3, and then just times 1. So a negative times a negative is a positive. The derivative of this is 1/3. So basically this is just another technique, another way of realizing that a definite integral can be used, a definite integral can be found by using u substitution. Now, we could have just gone back, like instead of here, we could have actually put in the u and then gone by our original 0 to 1. But this one, if you have a very complicated problem, you're able to do a lot more with this u substitution. So we're going to practice this in class. So I hope you watched the video and took good notes, and I will see you in class.